So for this question, it wants us to differentiate between discrete random variables and continuous random variables. The way how I look at it is looking at it from the perspective that discrete random variables considers discrete data. Now, discrete data usually involves data that's countable. So we're talking about, for instance, the number of people. I can have 5 people, 3 people, 4 people, and so forth. But it's an exact number. You're not going to go around and say you have 4.5 people on a bus. They'll look at you a little funny, like, huh? What do you mean 0.5 of a person is on a bus? Now, when you talk about continuous random variables, I think of continuous data. Now, continuous data usually comes from measurement. So stuff that you can measure. It could be either 15 grams heavy, it could be 15.45, and so forth when we are talking about these two. So in essence, to put it into perspective, we could say that discrete random variables are variables that represent discrete data and are counting numbers, whereas continuous random variables are variables that are in the form of continuous data, which usually considers things that are measured and not necessarily countable. So the number of people, and then for continuous, the mass of an object. So when we're counting people, we have to go 1 person, 2 persons, 3 persons, 4 persons, and so forth. If I'm checking the mass of an object, I would not necessarily say the mass is 1 gram, 2 grams, 3 grams. We usually measure the grams. And if I have a ball that is 15 grams, how do we know that it's exactly 15 grams? Depending on what we use to measure it, we could have 15.0005. We could have 15.123 grams. All of these are considered some form of 15. But depending on what scale we use, we're not necessarily going to get 15. On the other hand, now, if we have a person, no matter how we try to count a person, whether they're short, tall, whatever race they are, at the end of the day, we're going to have to consider a person to be a whole person. So we can have 1 person, 2 persons, and so forth, but we won't go around and saying I have a 2.0005 persons. Okay, so this is what differentiates the discrete variables versus the continuous variables. Alright, so for this question, it says that 40% of all tourists who attend a charity event will make a donation. 6 tourists will attend the event, and whether each one makes a donation or not is independent of the other's choices. Let X denote the random variable representing the number among the 6 tourists who will make a donation. So as you can see here, we have our 6 random tourists. Each of them have the potential to make a donation, and we have a 40% chance that these tourists who attend will make a donation. So out of these 6 people, just imagine they are all from different walks of life, and they do not care what the other person does. So their instinct to make that decision to give a donation is independent of the other tourists. No matter what the other tourists do or what they say would not affect the decision to donate or not of the other tourists. So we are saying that they are all independent choices of each other. So the first thing we have to do is state the probability distribution of X and specify its parameters. Now, X denotes the random variable representing the number among the 6 tourists who will make a donation. So we have a fixed number of people we can choose from. So I like to look at that as a cap. We have a cap on a number of people we can select from. So that is something that is a very important trait of the binomial probability distribution. And next thing is, they said here that the 6 tourists will attend the event, and whether each one makes a donation or not. So this donation or not means that they have 2 options. They can either make a donation or not make a donation. That is another assumption of the binomial distribution when it comes to probability. And another key thing that is important for a binomial distribution is that the scenario needs to be independent. So therefore, whatever the outcome is going to be independent of each other. So one decision in this case of a tourist should not impact the decision of another tourist. So just to give you a little refresher on the assumptions that binomial distributions make, there's a fixed cap on the number of potential trials. So in this case, we have 6. So n represents 6. So n is an important thing that we need to have. A next thing that we must have is a probability of success or failure. So it's only 2 options that we can have for that. So in this case, the probability for success would be 40%. Now we have to write this as a decimal to ensure that it's less than 1. So 40% is just 40 over 100, which is essentially 0.4. Okay, so that's the value of P. We could work out the value of Q, and it says the outcome of each trial is independent of the outcome of all other trials. So the fact that one tourist donates does not impact the decision of the others. So because of all these 3 assumptions that we find in the question, we know that is a binomial distribution. So we have a number of trials, which would be 6. We know the outcomes could either be success or failure. So in this case, it could be P, meaning that they decide to donate, or Q, meaning that they decide not to donate. And the outcome of each trial is independent of each other. So the outcome of the trial does not impact the other. So back to this question now, I can say that for part I, X has a distribution that is a binomial distribution, which is usually written like this, NP. Now in our case, we want X to explain why it's a binomial distribution, but I explained to you using the context why it is a binomial distribution. That's the only way we will be able to state that it's a binomial distribution. So in this case, I could say that the probability distribution is a binomial distribution. Now, we indicated as a binomial distribution. Now we need to state the specific parameters. So in this case, the parameters for this would be n. So in this case, n represents the cap that we have, which is one of the assumptions made in a binomial. We have a cap on the number of tourists we can have. So in this case, we are only looking at 6. So 6 is our cap, therefore n is equal to 6. Now as it relates to P, that is the probability of success in this case. So what does success mean in this case? We could say that with this, P means the probability of success. So in this case, success means will make a contribution. Now in this case, it said that it's 40%. Now 40% can be written as this, but remember we worked out that P is equal to 0.4. So therefore, the parameters of this would be X bin. We would put 6 here. The probability would be 0.4. So this would be our final answer here. But since we're gonna need it for the calculations, let's talk about Q, which represents the probability of not being successful. So in this case, Q is will not. So they will not make a contribution. So then Q in this case would be equal to 1 take away 0.4. Why is it 1? Because the probability could only equal to 1. So if 0.4 is the probability of success, that must mean that the probability of not being successful would just be 1 take away 0.4, which in this case is 0.6. And that's the first part of the question. For this number 2, it says exactly 5 tourists will make a donation. So we want to figure out the probability that exactly 5. So in this case, X, which denotes the random variable representing the number among the 6. So the number among the 6 in this case, based on this question, is exactly 5. So the probability that we're gonna have 5. Now, when we are doing binomial distribution, the formula for the probability can be written as this. So in this case, it would be NCR multiplied by P to the power of R times Q to the power of N. So in this case, what that would mean is that we could replace R with 5. N, we know that N is 6. P is 0.4. Q is 0.6. So in this case, we could say that the formula is going to be 6C5 multiplied by 0.4, because 0.4 is P, to the power of 5 multiplied by Q, which is 0.6, from here to the power of 1. So when we get this out, we'll end up with the answer. So this value would give us 36864. So this would be 0.036864, which would be approximately 0.0369. Now I'll explain to you what this formula is doing in the background when it comes to the actual application of it. So use these images to assist us with understanding what is happening in the background, but we'll essentially get the same answer. So if you're interested in seeing this, you could continue watching this next piece. If not, you could just skip forward to the next part where I'll answer the next question. So we have our 6 tourists here. We are saying that out of these 6, exactly 5 will make a donation. So let's put that into context. Let's see if we could actually figure out how this can occur. So we could say that this first one makes a donation. So tick meaning they made a donation. This one made a donation. This one also made a donation. This one made a donation. Let's say that this one made a donation. So we have exactly 5 so far. But say this one did not make a donation. So what we have now is a situation where we have 5 people who made a donation and 1 who did not make a donation. Now the issue is there are several different ways that this could occur. We could have had a situation where this person did not make a donation, but this one made a donation. So we have to account for each and every single possibility. So I'm showing you what happens with the use of the formula for probability when it deals with binomial. I'm showing you the long way how it is done to show you what happens in the background with the formula. Then we'll just use the formula to see why it makes things easier. So let's see if we consider each and every scenario. We need exactly 5 tourists who would make a donation. So we have this here 1, 2, 3, 4, 5, and then this guy won't make a donation. So let's look at these other scenarios. So we could have a situation where this one makes a donation, this one, this one, this one, not this one, and this one. So we now have 5 exact situations again. So remember, we have 6 tourists that will attend the event, and in this case we're saying that out of these 6, what if exactly 5 will make the donation? So in this first scenario here, 1 does not make the donation, the last one does not make the donation. In this one here, the second to last doesn't make the donation. This one makes it now in this option, this one, not this one, but these 2 make it. So we have again 5 people who actually did it. So as we keep going along, we would see a little story playing out here. So as you can see here in this case, we have 5 of them who did it except this one. For this one here, same thing. This one does not make it, this one does, and so forth. In this case, this one doesn't, and the rest 5 do. So what these scenarios show us would be all the possible ways that we could have a situation where we have a missing person. We have 1 person that actually does not donate. Now, how does this play into the probability? Now, what this means is that each person that actually contributes, their probability would be 0.4. So everywhere I put a tick, I can replace it with 0.4. So here is 0.4, and because it's independent, it's just like the things that we learn in the intersection when we have an intersection in probability. So for instance, PA intersection B, once they are independent, we would say the probability of A can be multiplied to the probability of B, which accounts for both of them happening at the same time but are independent of each other. So from this point of view, this person was successful and contributed, so did this one, so did this one, so did this one, but this one here did not contribute. This one here did not contribute, so we would have 0.6. So in essence, as you can see here, we have 1, 2, 3, 4, 5 successful situations, and in this case we have 1 unsuccessful, meaning that this 1 person does not contribute. So if we was to do this for this entire thing, so if we wanted to find the probability for this first section here alone, we could just multiply 0.4 times 0.4 times 0.4 times 0.4 times 0.4 times 0.6, and once we do that in our calculators, we will end up with 0.06144. So let's say now we were to replace this tick here with 0.4 as well as these others, and the rejection we do it with 0.6, meaning that this person did not donate. What we'll end up with is 0.4, donator here again, a donator here again, not donating here, another donator here, and if we do the same thing that we did up here, we'll end up with the same answer, 0.06144. So I did this to show you that no matter what combination we have of these people who are the 5 tourists, we will always get 0.06144. And remember, with this here, when we arranged this, we literally thought of every single scenario that would get us exactly 5. So we have 6 different situations that would give us exactly 5 making a donation. So therefore, we could say that if we're gonna get this all the time, every time, consistently, no matter how we select these 5 people that's gonna do it, all of these consider all the possible possible outcomes. So there is a scenario where we consider every scenario for the person who does not select. So in this case, this person doesn't select, this person doesn't select, this case, this one doesn't select, this one doesn't select, this one doesn't select, and so forth. So if we multiply 6 by this 0.06144, our answer would give us the probability. So when we multiply this, we'll end up with 0.36864. Now, I could just round this off to 3 decimal places, which would basically be 0.36. This 8 turns to a 9. Now, if we go back to our formula, the probability for the formula is NCR multiplied by the probability to the power of R times the probability of not being successful, and then we have N minus R for that. So in this case, we are looking for the probability of exactly 5 being selected. Exactly 5, because 5 represents the number among the 6 who will make a donation. So 5 will make a donation. That is what this X here in this case represents. So now if we put this into our equation, we'll end up with, we know that N is 6, so we could say 6C. In this case, we're using R as 5, multiplied to the probability of success, in this case 0.4 to the power of R, which would be 5, multiplied by Q, which is 0.6, so 0.6 to the power of N minus R, which would be 6 minus 5. So now if we was to put 6C5 in our calculator, we end up with 6, which essentially matches this 6 here. This 6C5 represents the total number of combinations that we could have had. We considered each and every single one here already. So what this formula does, it kind of saves us from going through this headache of trying to determine every single possible option. Then when we're done, we multiply this to 0.4 to the power of 5 times 0.6 to the power of 6 minus 5, which is essentially to the power of 1. So then we would have 0.4 to the power of 5 times 0.6 to the power of 1. Now this here, when we put this in the calculator, it's the same thing as this over here. Why? Because we have 0.4 to the power of 5, which is the same as 0.4 being multiplied to itself 5 times. So we have 0.4 times 0.4 times 0.4 times 0.4 times 0.4, which accounts for this, times 0.6 to the power of 1. Alright, so this tells us the probability of selecting 5, and this number here tells us the total number of ways that we can make that selection. In this case, we have 6 different selections. So this here, if we was to put this in the calculator, this would also give us this value here, which is essentially 0.369. So hopefully that analogy makes sense as to what happens in the background with this actual formula. Third one, we want to say now at least 4 tourists will make a donation. At least 4 tourists. So what do we mean by at least 4 tourists? So when we say at least 4, if I was to tell you bring me at least $4, what would you think that means? So essentially what that means is you're bringing either $4 or more. So in this case, we have to remember that we have a cap at 6, meaning remember we have 6 tourists, so we cannot go higher than 6. Remember, binomial distribution with that probability always has a limit. You know, we have a fixed number. So this fixed number in this case is we're looking at just 6 trials. So we want 4 or more. So that would be the probability of X being more than or equal to 4. So in this case, what we can do now, we could figure out what more than or equal to 4 means. So what that would be is the probability of X being equal to 4, or the probability of X being equal to 5, or the probability of X being equal to 6. Now these are all our different possibilities that fit the question at least 4 tourists will make a donation. So we have X being equal to 4, X equal being to 5, or X being equal to 6. So in this case, we already worked out 5 from our previous question. So we know that that's set, which is 0.0369. So what we need to figure out now is when X is equal to 4. So we'll use this same formula here, and in this case we will say that N is 6. So 6 C4 multiplied by the probability, so 0.4 to the power of R, in this case we have 4, multiplied by 0.6 to the power of 6 minus 4. So if I simplify this, I'll end up with 6C4 times 0.4 to the power of 4 times 0.6 to the power of 2. So this will give us this answer, 0.13824. So then the next one now we have for 6, so exactly 6. So in this case, that means everybody who is a tourist is actually donating. So in this case, we could say 6C6 multiplied by 0.4 to the power of 6, because everyone is selecting, times 0.6 to the power of 6 take away 6. So then that will leave us with 6C6 times 0.46 times 0.6 to the power of 0. We will get 0.0. So if I was to replace back this 0.0368 with my initial number, just to make it specific, 0.0366864. Now if I add these up, 0.1792. Okay, so that is the answer we get when we add up all three of these. So the probability of X being more than or equal to 4, or having at least 4 tourists that will make a donation, would be 0.1792. And that's our answer. So for this last question, it says at most 1 tourist will not make a donation. So what could be our situation for that? So what we can have is either 1 tourist, no donation. We could also have 0 tourists, no donation. So we know what the probability of not making a donation is, which is Q. Q is the probability of not making a donation. So we looked at that earlier. Q is the probability of not making a donation. Okay, so no donation, we know that is equal to 0.6. So if we put this here, this covers the at most 1 tourist will not make a donation. So we could have 1 tourist making no donation or 0 tourists making no donation, but we cannot have more than that. These are the only 2 scenarios that can happen. If we are making a donation from 6, what we are saying is that we could have a scenario where 1 tourist makes no donation. So let's just say we have this one makes a donation, this one, this one, this one, this one, but this one does not make a donation, Now, remember, there are different combinations that can happen for this. We could have several combinations for this one, like we discussed in our previous question when we discussed in our part 2 of this question. So note here that I'm not taking into consideration the different combinations. I'm just looking at how does this play out. What does 1 tourist with no donation means? Okay, so 1 tourist, no donation. So this is what this first one means. So essentially for that first part, 1 tourist, no donation, that's the same thing as saying, okay, we have the probability of making a donation, which is 0.4. Remember, this is the probability of making a donation, 0.4. Okay, now how many people do we have making a donation? We have 5 people making a donation and 1 not, because only 1 tourist is not making a donation. So this 0.4 would go to the power of 5 multiplied by the probability of not making a donation, which would be only 1. So essentially we'll be treating it like we did question 2. Okay, we did question 2 the same way, which is the probability of having 5 making a donation. Okay, so remember, in this case, the probability of success is making a donation. So I am just rewriting the formula to basically work out for the way how they changed the language. So 1 tourist, no donation would mean that I have 0.4 times 0.4 times 0.4 times 0.4 times 0.4, or essentially 0.4 to the power of 5, which is then multiplied to 0.6 to the power of 1, since it exists only once. Now, how do we consider the combinations? Now, we could do it from 2 perspectives. The first perspective is if we're saying, let's have 6 people and we are choosing the 5 that actually make a contribution. Once we put this in the calculator, we're gonna get 6. Okay, now what if we look at it from the perspective of 1 tourist making no donation? So what we'll end up with is 6 C1. And if we put that into the calculator, we are still gonna get 6. So either how, whichever perspective we look at it, in this case, we will for sure end up with the same value. So in this case, I could say 6C5, which essentially means that 5 will make a donation and 1 will not. So I'm looking at from the perspective of 5 people being chosen to make the donation. Even if I did it from the perspective of 1 tourist with no donation, I'll still end up with the same value here of 6, which would give me the same answer. Now for this here, the answer we know is 0.036864. How do I know that? Remember, okay, we worked this out already. So I know what it is for 1 tourist and no donation. Now the next one I need to look for is 0 tourists and no donation. So 0 tourists do no donations, right? So that means if 0 tourists are doing no donations, that means we're going to have 0.4, meaning donation, 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 donation. So essentially everyone is going to make a donation. So when I look at that from a perspective of 0 tourists, no donation, essentially that's like saying everyone is making a donation. So 0.4 meaning the probability of making a donation to the power of 6 multiplied by 0.6 to the power of 0, because this 0 represents that none of these here are making a donation. 0.6 meaning to the power of 0, meaning that 0 people are not making a donation. So essentially that means all of them are actually making a donation. And back to this same selections, how do we consider the selections? The same concept. We could either look from it from the perspective of all making a donation or none making a donation. So in essence, if I did none making a donation, that would mean we're choosing 6C0, meaning none make a donation, and this will give us 1. So likewise, if we used 6C6, this would also give us 1, okay? So whichever perspective that we look at it from, we'll get the same answer. So in this case here, that would mean that my answer would be the same as the one we did for 6. Remember, we did this earlier. We already did this, which would essentially be 0.004096. Now, no matter how you put this in your calculator, essentially it should give you correct answer. We could just add these together and that would give us our answer. So this plus this, which would essentially give me 0.04096. So to round this to, let's say, 4 decimal places, I would have approximately 0.0410. So essentially this 0 has no value, so I can leave it as 0.041. So final answer is this. So make sure you pay close attention to how we were able to work this out. Remember, we said there are multiple ways of getting this one, and in this case there's only one way that we can have all 6 selecting doing the donation, or in other words 0 not donated. Okay, so you have to be able to see it from both perspectives in order to answer a question like this. Alright, so for this particular question here, now it says the time taken by a secretary to type a 10-page document is normally distributed. So it has a normal distribution. So usually when we have a normal distribution, we're gonna have a mean as well as a variance. Okay, so the variance is basically just the square of the standard deviation. So it says that it's normally distributed with a mean of 125 minutes and a standard deviation of 5 minutes. So in essence, if we was to write the parameters, we would say we have the mean, which is 125, and we also have the standard deviation, which is 5. So this would be 5 squared. So now we could try to answer these questions. We have I determine the probability that the secretary will take between 118 and 129 minutes to type the 10-page document. So if I'm going to think of it from a normal distribution standpoint, I need to look at this. So it's normally distributed, and usually in the center here we have the mean. So the mean in this case is 125 minutes. Now we want to figure out what it would be to have 118. So let's say 118 was here. So we want it to be between 118 as well as 129. So we are trying to figure out what is the probability between here. Alright, remember, if you know anything about normal distribution, this entire chart would be representative of the probability of 1. So if we were to walk this out and go through the charts, we should be able to figure out what the probability of this section here. Now the thing here with this question is that when we do questions like this, we have to walk them out in parts. So this is telling us that we want a probability of the variable x being more than 118. We also want it to be still less than 129. So essentially we want to get this section. So now to get this section, we need to work out what the probability of getting less than 118 is, and then we also need to figure out what's the probability of getting less than 129. Now why is this important? If we could figure out what it is to get less than 129, so this area here, if we subtract this small little piece here, it's essentially like erasing this small section right here if we subtract it. And once we do that, look what we'll be left with this piece out here. Now bearing this in mind, let's work out the probability for each of these. Now what we need to do when we working this out is we need to go to the z-score table. But in order to go to the z-score table, we need to convert our data here into z-score values. Remember, we need to think of our data here, our raw data here, as being one currency. So let's pretend like this was EC dollars, and let's say we wanted to convert this EC to US dollars. How do we do this? If we want to go from converting EC to US, usually we get it from a friend, or most commonly we go to the bank. So the bank would be the bridge between converting the EC to US. So EC, we go through the bank to convert it to US so we could walk out with US. Likewise, we need to convert our charts here to a standardized form, which we will get from the z-score table, right? We will look at the z-score table to get these values. So what do we consider to be the bank in this case? The z-score formula, okay? Once we look at this here is like our bank. So let's call it the Z bank. Now, this is the EC that we have here. They want us to have X. So what value of X are we looking at? We are looking at 118. So for this first one, we're looking at 118. So we could say 118 minus, and then we have to subtract the mu, which is the mean. So that's 125. So once we got that, we divide it by the standard deviation, which is 5. So once we do this here, we'll end up with Z being equal to negative 7 over 5, or could call this negative 1.4. So having 118 in this case, if we convert it, it's the same thing as saying negative 1.4. So this part here represents negative 1.4. And in the center here would be 0. This is usually always 0. So in a while, we'll try to see what this means and get our values from the z-score. But let's look at this for now. So 129, like how do we find 129 and convert it into z-score by the Z bank? So what we have to say is Z is equal to 129, because remember 129 in this case, or this X value here, represents 129 here. Remember we said we'll find for less than 129, and we'll find for 118, and we'll subtract the probability of both of them. So 129 take away 125 divided by 5 would leave us with Z is equal to 4 divided by 5, or 0.8. So that must mean that the value out here in z-score terms is 0.8. Okay, so let's actually go to the Z bank and see what we get transferred. So let's look at our first one, which is less than 0.8. Now, just to bring a little context to this normal distribution, if you look at this, anything on this side is worth 50%. Likewise, anything on this side is worth 50%. So anytime we have something that has more than 50% shading, we know that our probability should be more than 50%. So in this case, as you can see, this is my halfway point, and as you can see, more than 50% is shading. So when I look at my answer, I should get a value that is more than 50%, or more than 0.5. So for the probability of X being less than 129, based on our actual 0.8 in the z-score table, we would, for 0.8, we have to look along this here for 0.8. So we look for 0.8, and since we didn't have any number after the 8, we just had 0.8 flat. That means we have to look for 0.80. So 0.8 here, and the second decimal place would be the 0 here. So we'd have 0.80. If for instance we had 0.84, we would have been looking here 0.8, come along here until we reach 4. So in this case 0.80 or 0.8 matches with 0.7881. Therefore our probability for here would be 0.7881. So this area here represents 0.7881. Now for this case, now we have to look for the probability of being less than 118, or in other words less than negative 1.4. Now when you look at this here, now we do not have a negative 1.4. For the paper that they give you for the CAPE exam, it does not show you the negative versions, it just shows you positive versions. Now the thing is, this normal distribution is symmetrical, so meaning that if we have less than negative 1, that would be the same thing as having more than positive 1. So in essence, because this normal distribution is symmetrical, if we could work out what the area of this is, it would be the same as the symmetrical side of it over here. I know my drawing isn't as accurate, but I'm just using it to let us know that if I have negative 1.4 here, the answer for this here would be the same as if it was over here, which would have been positive 1.4, because these are symmetrical. So if you look at negative 1 go to the left, it would be the same area as this positive 1 here go to the right. Now this chart only shows us anything that's less than. So less than. So what I need to do to figure out what is the area here, I need to figure out on my chart what is less than 1.4, which would be this whole area here. And remember in the beginning I told you that the entire area under this curve is equal to 1. So if I could figure out what my chart says about this less than 1.4, I can just take my answer and say 1, take away that answer, and I'll know what this small little section is. So 1 take away for whatever I get for less than 1.4. So let's look for what the value for 1.4 is. Now if we look here, we say 1.4 is here on the z-score, so 1.4, and then over here now is 0. So 1.40 is 0.9192. So that means everything here on this green side is 0.9192. So in order to figure out this small piece here, I need to say 1 take away 0.912, which would give me the area for inside here, which is essentially the same area of inside here. So the answer for this would be 0.0808. So that's the probability of this shaded region, which is also the probability of this. So the probability of x being less than 118 is 0.0808. Now remember what we said. Now to find the section in here, we need to subtract these two values here. So in essence, we need to say 0.7881 minus 0.0808, which is equal to 0.7073. This one says that the probability that a secretariat takes less than t minutes. So the probability that the secretary takes less than t minutes. We don't know what a t minutes is, but we know that it represents 0.9686. 0.9686. So if I want to sketch that on a diagram, remember we said earlier, anything under here represents 50%. And I was saying less than, so we know we're going to be shading to the left. So this says 0.9686, so we know this has to be more than 50% or more than 0.5. So therefore my t cannot be on any side on the left here. It has to be somewhere over here. How do I know it has to be somewhere over here? This is more than 0.5, which means that if here is 0.5 down representing the area, we need a value that passes this right here, which would be 125. So our value should be higher than 125. So let's assume that this whole area here represents 0.9686. So that means that we have an area that's 0.9686, and even though this is not drawn to scale, we're just saying that the part that's shaded represents 0.9686. Now remember, in order to figure figure out what this value is, like we did earlier, we need a converter. We need a bank. So our bank is the z-score is equal to x minus mu over standard deviation in order for us to figure out what the value of t is. So we are saying here that what we did is we have some z-score. We don't know what that z-score is as yet, but this score, when it's less than that score, that z-score, we have an area that is 0.9686. So the first things first, I need to figure out what my z-score is. I know that the probability is 0.9686, so I need to look on my chart to see where 0.9686 is. And the good thing is I know that we are looking at the less than side, so therefore I wouldn't need to do any conversion later, because remember this chart shows less than. Okay, so I need to look for 0.9686. So we look around for these values, see if we see it. So I have 0.9664, 78, 0.9686. So thankfully it's an actual number that already exists here. So 0.9686 would represent 1.8, which intersects with this 6 here. So therefore our answer for that z-score would be 1.86, because 1.86 gives us 0.9686, meaning that the shaded region that we just found to the left would be 0.9686. So in essence, the value here for the z-score represents 1.86. So if the z-score is 1.86, we could use it into this equation now. So we know the z-score, which is 1.86, and that's equal to what? X, which is x, the value here, t, that we are trying to find. So I can replace this with t minus mu, which is 125. And this 125 represents the mu. So we have t minus 125 over the standard deviation, which is 5. So then now, if I put 1.86 as a fraction, which is itself over 1, I can cross multiply to solve for t. So then if I cross multiply, I would say 1.86 times 5, and then this entire thing at the top multiply by 1. So we'd have 1.86 times 5 is equal to t minus 125. So 1.86 times 5, once we work that out, 9.3, which is equal to t take away 1.125. Now, to get t by itself, we add both sides by 125. So then we'll end up with 9.3 plus 125, which is equal to t. So therefore I know that t is equal to 125.9.3, which is 134.3. And this unit we have minutes, so 134.3 minutes. As you can see here, we have the value for t that shows you the probability of anybody getting under this time would be 0.9686. So remember, we had to use our conversion, so we took the probability from here using our z-score, took it to the bank, and then the bank helped us to get our money back in a different currency. So in this case, our answer is 134.3 minutes.